That was a really nice intro. All right, who's here to talk about databases? Some folks here to talk about databases? Anybody? Woo! All right, come on, wake up, let's go. I know it's 9 in the morning. I know. I appreciate you. I appreciate you for being here. All right. My name is Joey. I'm here with Ayushi, and we're going to talk about migrating databases safely at millions of requests per second. Thanks to Joey's intro, I think we can skip this. I'm Joey. That's Ayushi. And today we're going to be walking you through kind of a story of why we have to do data store migrations, and then when we have to do them, what are our techniques, and like how can we really design our systems to be migratable in a zero downtime, in completely up way. And then finally we'll close with a couple of case studies that kind of show you the power of this general system and how we can apply the same techniques to different migrations and have them all be safe. All right, so let's start with the problem. The problem at Netflix is that we have a lot of state, and it's all over the world. So every red country on that map is a country that uses Netflix, and then the purple dots there are where we store copies of our data. At Netflix, we use 4 Amazon regions with 3 availability zones each, which means that we have 12 copies of data spread across the world for almost all of our user data. Keeping all of this consistent is tough. Why do we do it? Well, we do it because of the scale. We do it because we have massive volumes of traffic to these data stores, massive amounts of data to store in these data stores, and our developers expect single-digit millisecond, or in the case of some of our caching layers, less than a millisecond at all times. So we just wanted to kind of show you the reason why having safe data migrations, being able to change these data stores is so important to us, because we just have a lot of them. And if we don't make it safe, we're going to make mistakes, and nobody wants the Netflix to not work. That would be a bummer. But it's more than just scale. It's also that the solutions that you can use to solve problems overlap. So I like to talk about this like universe of database requirements. So at Netflix, we have lots of microservices. Those microservices have some requirements, and those requirements fit in this kind of picture. And you'll notice that the different solutions, like a key value store or a relational store or a blob store, they overlap. Some use cases can be satisfied by multiple options. And at least at Netflix, we have use cases that span all over the place. Some of them can be handled by multiple stores. Some of them have no solution, and we're very sad. And that's where the data platform team that we work on comes in, because sometimes we can build a solution. But sometimes there isn't a good solution, and sometimes there are more than one solution to the same problem. But it gets worse, because it turns out that use cases aren't static. They don't stay the same. For example, here we have a use case that started off, and we could have picked a key value store, a relational store, or a blob store to satisfy that requirement. But then over time, as that application evolved, it became only satisfiable with a blob store. We had a 2/3 chance of picking wrong, and we would have had to migrate them. But you might ask, like, well, what causes that shift? And at least at Netflix, it has to do with different features or products shifting their demands. So for example, over time, maybe a service gets more popular, gets more traffic, or maybe they just are accumulating data over time and the storage goes up over time. So as these things scale, that's what causes those use cases to kind of move around the universe of database requirements. Who here has had a case where you picked something, like picked a data store, and then 2 years later you were like, oh man, if only we'd picked the right data store? Anybody? Yeah, we've got a couple folks. Okay, a lot of folks. That's good. This talk hopefully will help you then. It's not just the use cases changing though. The offerings change too. Amazon is constantly releasing new capabilities. For example, I've picked 3 here, the DynamoDB global tables, the Aurora global data store, and S3 strong read after write consistency. These were 3 announcements from Amazon which really enlarged the span of problems that offering could solve at Netflix. Which meant that even if your use case stayed exactly the same, it's possible that with a new change to an offering that you might have to migrate as well. And then finally, there's cost. Because it turns out that pricing is another aspect of dynamicism here. In particular, as you scale, the cost trade-offs between managed services and self-managed services change. On the x-axis here, we have like this kind of numerical measure of scale. There are a lot of factors that go into scale. On the y-axis, we have how much money that costs. And you'll notice that like that fully managed service starts off at 0 cost. That's fantastic, right? Like you don't have to deploy any infrastructure, you don't have to pay any engineers to set stuff up. Contrast that with a self-managed option where maybe you have to actually like write some controllers or build some expertise. And in that world, there's a high initial cost. As you scale, though, it's often the case that that fully managed service scales at a higher rate of cost, which means that even if you pick the right thing at the initial level of scale, as that use case scales out, the correct choice might change. And this is dependent on pricing. The good news, at least, is that that question mark percentage mark, that's like saying what frequency, how many use cases fit under this. At least at Netflix, that number is actually quite high. And if you have the ability to move between these, then you can use the optimal engine for price performance for everyone. You know, we like to joke that this was the year of efficiency. How many people had like an efficiency effort this year? Yeah, a lot of people. We did too. And a lot of it was understanding these curves, was understanding where could we choose a better data store to serve a particular use case and save dollars. All right, so we've just done a lot of motivating of like why you might have to migrate. I do want to caution that you really should avoid doing database migrations if you can. So for example, if you're just doing software updates or if you're just doing kernel updates, you really shouldn't move state around. Instead, I highly encourage you to check out the talk that our colleagues gave yesterday, NFX305, on how to iterate faster on stateful services. They showed a lot of really useful techniques for how to avoid data migrations if all you're doing is touching like software or hardware. But sometimes you must migrate. So when you must, understand how to do one, automate that migration, and automate safety into every migration, and then we're going to execute those migrations in parallel. And that's going to be the key. All right, so let's dive in and let's see some techniques that we can use to migrate state when we have to. All right, we're going to do a three-step process here. First, we're going to abstract the underlying storage API. And this is because it's hard to migrate data stores if your applications are strongly coupled to those data store APIs. So we're going to figure out how can we decouple the applications from those underlying storage engine APIs. Then we're going to shadow traffic idempotently, and we'll go into what that means more in a second, across both writes and reads. And then finally, we'll merge those in-flight writes with backfill data in an idempotent fashion and verify that the new data store has the properties that we expect. To kind of take this and break it down into pictures, we're going to follow this. We're going to start by setting up a client that sends traffic to some type of proxy. That proxy forwards the traffic to an implementation, which stores data in our database. The first step of setting up that shadow is setting up a second implementation, which writes to some other database, and then have our proxy layer kind of duplicate that traffic. And the reason the lines are dashed there is because we want to indicate that you always want that side to kind of be a shadow or dark launched. Because typically, at least in my experience, sometimes the shadow breaks because there's something that you didn't think about. And if the shadow breaks, you don't want it to bring down your real production workload. Third, we're going to initiate a backfill where we copy all of the data out of database 1 into database 2. And we have to copy it in a way that's idempotent and merges with the writes that are coming in from that second implementation. Otherwise, we're going to end up with database corruption, and nobody likes database corruption. Once our monitoring says that this looks good, we can promote and switch traffic from primarily being served by implementation 1 to implementation 2. And you'll notice that we didn't remove implementation 1. Because even after all the verification that Ayushi is going to talk about between those two stages, sometimes something still goes wrong, and you want to be able to quickly roll back to implementation 1. And then finally, if everything looks good, we can decommission. So this is the full picture. And this talk is going to walk through each one of these steps and show you how to do them. All right, let's get started. I'm excited. You guys excited? Yeah? All right. So how are we going to set up, like what do we actually mean by like a client talking to a proxy and implementation? Well, at Netflix, we like to use this thing called a data abstraction or a data gateway. And what that is it's an API that the data platform team owns. So we define that get items and that put items API. We operate that data gateway service and implement a translation layer that takes those get items and put items calls and then translates them into the database specific APIs. So for example, here we have Apache Cassandra. We're taking get items, we're translating that to select queries, we're taking put items, we're translating that into insert queries. But the really cool thing about this is that we can change everything on your write. We can change the data store, and the client, the application, doesn't know. The application is still calling get and put. For them, the data store hasn't changed. So this is an example with DynamoDB where we're translating puts to, for example, batch write items. All right, but how does that API really look? Like, that sounds nice in theory. What's it look like? Well, this is the key value API at Netflix, and the data model for the key value service is a hash map of strings to assorted maps of bytes and bytes. And we'll get into a bit why that sorted map is so important. And we essentially just have CRUD here, right? We have put, we have delete, we can do get, and then we can scan. Get returns all the items within the inner map, scan returns all the ones on the outer. If you guys have used DynamoDB, this hopefully looks kind of similar. It's like kind of the same idea. But it has a couple of key concepts embedded. And one of them is these idempotency tokens. All mutative operations in our data APIs take these idempotency tokens. What is an idempotency token? Well, it's a mechanism for us to be able to replay writes and know that those writes deduplicate. So in this example, we're writing some values into this X register. So write X equals 1 at token 1, write X equals 2 at token 7, and so on and so forth. And then our data store is resolving conflicts by always using the latest token. Different data stores resolve conflicts in different ways. You might have to actually like model it into your data model for this to work. But for example, in Apache Cassandra resolves writes using last write wins. So what that means is that the last write on that put X equals 1, time equals 1, it doesn't change the value of X. Because when it kind of deduplicates with that write before it at t equals 12. Specifically, because t equals 1 is less than t equals 12, the database does not update the value. So broadly speaking, idempotency tokens are kind of the pseudocode. We get some token that depends on the data store. We send a write with that token, and then when we're duplicating it to another data store, we make sure we send the same token so that we can kind of merge those streams. So what does that look like for a last write wins token? It's pretty simple. You can just kind of get the timestamp, add a random nonce, and then we like to mix the random nonce into like the last digit of the microsecond timestamp, just to kind of increase the probability that things are different across machines. And you might say, but Joey, you've violated a pretty important rule of distributed systems. You used a clock. Everyone knows clocks don't work, right? Well, in our experience, they actually work really well, especially since AWS Nitro. So EC2 Nitro has brought clock delay down. As long as you're using like the most recent kernels and you're using like the proper NTP daemons. This is real data from the Netflix fleet of over 20,000 EC2 instances across 10 different instance families, all using Nitro. This is clock delay, essentially a measurement of clock accuracy. That's phenomenal, right? Less than a millisecond of clock delay. Clocks are pretty accurate. The bigger problem is actually precision. It's that you want a microsecond level timestamp, but you can only get a millisecond one because Java's amazing. And but at Netflix, what we found is that a lot of these arguments aren't really made with modern cloud environments in mind. They're made with like non-modern, like let's be honest. Amazon has like atomic clocks and GPS stuff. Like you don't have that stuff. Amazon has that. It's really useful. Use it. It makes your job easier. All right, so we've talked about writes. We've talked about how to make those tokens. But what about the reads? Because when you're designing for APIs to be shadowable, you have to think about the reads as well. We don't want an API that just returns giant amounts of data, which for you to then compare requires you to like load gigabytes of data into memory or something. Instead, we want to figure out how to break down those read APIs and kind of paginate through yielding items. So here's some pseudocode of the KV get items API. It returns a page of items, usually about 2 megabytes. And then the service returns a page token saying, hey, there's more data. You have to keep reading. Now, why is this important? Why is this important for shadowability? It's important because most data stores return pages of results using some kind of database-specific cursor. So for example, like if you're using a SQL database, there's usually some like particular cursor implementation for that particular result set. But when we're shadowing across data stores that maybe have different mechanisms of resumability, we have to build resumption into the API. So how does that work for key value? Well, it takes advantage of that sorted map. Because sorted maps are resumable. All you have to do is record the last key that you returned into the token, and then no matter what the implementation is, whether it's SQL, whether it's Cassandra, whether it's Redis, you can equally resume a read query from that position in the sorted map. And this is actually something that I think is not super intuitive, right? Like you think, well, like obviously, like I can just resume the query. But in practice, you have to think about these things before you get into the migration. Otherwise, you're going to be trying to compare these massive result sets, and you just won't be able to build the confidence that the two parts of the shadow are functioning the same. All right, so we've seen how to make our APIs ready for migration. We've seen on the right side that we've made every mutation in the system idempotent with idempotency tokens. We've talked about breaking down work on the read side into fixed size work, not count, with resumable pages. The same principle actually applies to writes as well. For example, if you have like a very large value, you want to break it down. A lot of APIs do this through some form of like chunking or partitioning. For example, S3 has like part numbers, right? Like those are chunks. Those are just breaking down larger values into smaller ones that make them individually retriable. And now that we've made our APIs, our data APIs, ready for migration, now let's dive into actually doing the migration. And for that, we need some shadow traffic. All right, what's shadow traffic? That's step 2 in our diagram. And shadow traffic is where we start capturing all of the get items, put items, scan calls, and we start sending them to the second implementation in a shadow mode. Which means that the primary implementation, implementation 1, is responsible for actually answering the client, but we're sending the traffic to implementation 2 and getting that data into the data store. And again, at Netflix, we like to do that using the gateways. So for example, here, we see a put items call hitting the data gateway, and then the data gateway is duplicating that traffic between an Apache Cassandra CQL implementation on the top and a Thrift Cassandra 2.0 on the bottom. I'll forgive you if you don't know about Apache Cassandra Thrift. It's a really old version of Cassandra. We'll talk about later how we finally got off of it after a decade. But you'll notice, though, that we're translating the same put items call into these different APIs, into the batch mutate or the insert into. We can also do that for other data stores. So for example, if we're doing a migration to DynamoDB, we can use a batch write item. And sometimes we can't use the service because that like general purpose API we've designed is not general purpose enough for a particular service. We would say that at Netflix it's about a 90-10 split. 90% of users can migrate using our well-defined APIs. 10% have like these really weird data requirements. So for those, we take the same technique, but we bring it into a library in their actual code base. So here you see that kind of like bridge impl that's then duplicating to the key value data access object and the Dynamite data access object. Dynamite is just a Netflix like Redis system. So it's like a Redis compatible proxy. And you can see here that we can use the same technique even though we don't have that separate server. We can still have that bridge interface. We can still have those two implementations. And we can still translate what the client is seeing into those backends. We can do the same thing for writes with a library. Here is an example with Cassandra and Thrift again. And then, of course, we can also shadow reads using the gateway technique that we talked about earlier. So in this case, we've got a get items, and again, we're translating it between CQL selections and Thrift get slices. And we can shadow reads in the library. So we can kind of see how this kind of like shadow mode plus 2 implementations or more can be generalized both within a server and to libraries that implement arbitrary interfaces. Sometimes you have to do library-based migration for the reasons that I talked about earlier. But really it boils down to library-based migrations can support any bespoke interface, like any interface that you can define in your programming language. You can use a library-based migration. However, the reason that Netflix generally tries to avoid library-based migration and instead use those gateways is because when you have the library implementation, there's a lot of bad stuff that can happen. So for example, the shadow can impact prod. What do I mean by that? Well, because your code is running in the same like JVM or other like execution environment, they can impact each other. So for example, if you have a bug in your new code that's talking to the new data store, that bug can actually bring down your good code that works. Who's ever deployed a bug while doing a migration? No, oh, come on. Me? I've done it. It happens. And when you do that, the problem with the library-based technique is that those bugs can bring down prod. So we try to avoid this if we can. And when we have to, we try to be very diligent about the implementations being safe. We also have to add kind of bespoke insight. Because this isn't a service layer, we don't have the out-of-the-box inter-process communication metrics that we're very used to in Netflix, and which we'll talk about later, are very useful for verifying that the two sides are equally performant. It's hard to quickly iterate, and it's hard to promote the primary in a quick way. So for example, you have to build some kind of control plane into this library so that when you're ready to promote, the window of promotion is as narrow as possible. So for all of those reasons, we try to avoid this, but it is always there as a kind of backdoor backup option if you can't use the gateway approach. All right, and with that, I'll hand it over to Yushi, who will talk to you about backfilling.
Thank you, Joey. So, shadow writes will take care of writing the new data to the new database, but we still need to copy the data from old database to the new one. And for that, we use the process of backfilling. So in order to backfill the data, we read from source database, do some transformation on it to make it compatible with the target database, and finally write to it. During this entire process, we don't want to overburden the system. That's why we have a throttling mechanism to control the data flow at source and target. We control the reads, the rate at which we read the data at the source database by looking at the read latency metrics, and we control the write throttling by looking at the CPU and the disk usage at the target database. So for backfilling, we don't always have to use the database to read data from. We can make use of our backups. In Netflix, we upload backups of all data stores to S3, and we'll use those backups to read the data and finally write it to the database. In this case, we are dealing with backups, so we don't have to throttle our reads at all, and it can be faster. We can also avoid write throttling if we can write directly to the backups and then use a bulk loading functionality to copy the data to the target database. Once the data has been backfilled, we need to verify the data for its correctness, as well as we need to verify the performance of the system. And it is a very important step before we can promote a secondary database to become the primary and serve the production traffic. So in order to verify for the correctness, we have two methods. We have used two methods to do it. Either we can use the online comparison using the read queries, or we can do the offline comparison using the backup snapshots. So to do the online comparison, we read data from both the databases and compare for the difference. We have used scan at the source database because in this case, we want to do the massive retrieval of the data, and scan is very efficient for it. But we have used get at the target database because we want to query the specific row using the primary key. But you all might be wondering, why can't we use the scan at the target database? The reason is, when we backfill the data from one database to another, we promise the presence of the data, but we never promise the order of the data. So if we do scan at the target database, the order of the data might be different than the source one, and hence it can result in an inefficient comparison. Yeah. So for offline comparisons, we'll make use of the backups. So what we do, like backups of the source in the target database will be there in S3. So we'll read the snapshot for the same time for those both databases and download it to Hive using the Spark job. This is the responsibility of Spark job to do the data checks and populate the differences so that we can look at the specific rows where the data is not in alignment. And the backups can also be used for the functionality comparison. Suppose, let's say we want to release a new version of a Spark job. We want to make sure that the new version works as expected. So what we'll do, we'll pass the same backup snapshot to the old and the new job, and verify for the difference. If the outcome of both the jobs aligns, we are good to release the new version. But if there is any discrepancy in the data, then we might have to go back and fix the bugs in that case. This is just an example of one of the Spark jobs which we have at Netflix. We have a stable version which is used for the benchmarking. We have a Kennedy version which is basically the system under testing. And there's a comparison setup where we basically populate the results of the difference of the two systems. So now let's highlight some key differences between online and offline comparison. Online comparison is very, very efficient for a smaller data set. If we try to perform it for the larger data set, then it might place a huge burden on the system and degrade the performance of it. It is also closer to what client observes because it just points to the real-time data which is in the system, unlike snapshots or backups which may or may not be updated. Whereas, if you want to do a comparison for the larger data sets, offline comparison is the way to go. It will help us in dealing with a massive amount of data in the background by doing the data loading, restoration independently and concurrently without affecting the performance of the live cluster. Because we don't interact with live cluster at all, so we don't have to worry about the performance degradation in that case. So what is the best way to do the correctness verification? I would suggest combine both. We should always verify for a small sample of data using the online comparison. And once we have enough confidence, then we can do comparison of the 100% of our data using the offline comparison. Now let's talk about verification of performance. Again, there are two ways to do it. Either we can use the online using the read and write latency metrics, or we can use the offline way where basically we have used canaries and the profile reports. So in order to do the online comparison, we have dark launched not only our writes, but our reads as well. What does it mean? That basically when an application sends a query, the data gateway will take care of sending it to both the databases. But it will use the result of the database 1 to serve the traffic of the application, and the result of the database 2 will be disregarded. But then why do we need to perform read and write on database 2 in the first place? The reason is to gauge the performance. It will help us in understanding the latency differences between the two systems and how can we make it better. So this is an example of read latency, and we have also computed this thing for the write latency. And if we see that there's a huge difference, we can do some adjustments and check in the real time that whether those adjustments are reflected into the latencies at all. But can you imagine doing this for hundreds of clusters manually? If that were the case, we would have submitted this talk for reInvent 2024. So that's why we automated the entire process using canaries, where it will use the old system as the stable benchmarking system and the new system for the testing system before we can do the full-scale rollout and gauge its performance. So this is an example of the canary which we have used at Netflix, where we can specify different metrics which it should monitor for the performance evaluation. And we can also specify that if the performance is not as expected, what should be the outcome, whether it can alert us or it can completely fail the system. So this is just an example of a canary which has used these customized parameters and failed the performance evaluation for our system. We have also used CPU profiles to find out the bugs. These are the few issues which we figured out. We have realized that there were few queries which were not optimally compiled, and they were using a huge amount of system resources, leading into inefficient processing. We have figured out few serialization, deserialization issues. We have realized that we were doing over-allocation of the resources, which was leading to frequent garbage collection cycles. We have also used CPU profile to compare the processes side by side. As you can see in this example, we have two processes running. One is the SQL process and the other one is the thrift. And we use CPU profile to find out the performance of it. And after the evaluation, we realized the SQL path is taking 30% time on the CPU, whereas the thrift path is taking 13% time of the CPU. So what is the entire cycle to get to the promotion? So basically, we start with a shadow launch. We'll shadow our reads and writes. Then we'll backfill the data, and then we'll monitor its performance. If we are, when we see that, okay, there are no issues, then we'll try, if there are issues, we'll try to fix them. And then we'll try to fix and monitor it till the time we see no issues. Once we are confident, we'll promote our secondary to serve the read-write traffic. At this point, we still have our old database. We have not decommissioned it. And then we'll see the performance of the new cluster. If we see that there are any more issues with the new cluster, then because we still have our old database, we'll just roll back the read and write to the older database. In the meantime, we'll try to find and fix the bugs in the new implementation. And we'll continue this entire cycle till the point where we see zero regression, where we are confident that we are not seeing any more issues. And at that point of time, we are ready to decommission the cluster. And that brings us to our last step, where we have decommissioned the old cluster, and now the new cluster is solely serving the read and write traffic for it. So these are the steps involved to do the database migration, but this is just for the one migration. And now imagine the scale at which Netflix is operating, and we have huge amount of data which we have to move from one system to another, but not just for one system, but there are like thousands of systems involved in such case. So that's why I want to share with you all that in 2023, what we have accomplished so far as a part of our database migration initiative. We have migrated over more than 250 databases, which were impacting more than 300 applications, dealing with thousands of terabytes of data, and finally resulting into 12 different migration paths. And all this is possible because of the migration steps put together by the data platform team. Now we have done this huge migration, so I want to walk you through the few of the case studies that were involved, that were the part of these migrations. The first one is the Cassandra version upgrade. We recently migrated our entire Cassandra fleet from version 3.0 to 4.1, and the reason was that Cassandra 3.0 was reaching its end of life, and there are so many good features in 4.1 which our streaming platform could benefit from. What is the major concern in this migration? As we all know that when there are new upgrades, few of the properties gets deprecated, few of the properties gets added, and also in the new system, there could be a change in the way they handle a certain workload. So it was very important for us to do the configuration evaluation, performance evaluation. What is the strategy we followed? We used the shadow read and write process, and then once we are confident with the performance and the data correctness, we did the in-place upgrade of the system. So basically, we shadowed our writes using the data gateway, which took care of writing it to both Cassandra 3 and Cassandra 4. And once we did that for our test load, and we tried to see the performance of it. The performance, we saw that, okay, the new system is having more latencies, and it's not performing better than our old system. And we're like, okay, it's not too bad. Probably we can test it for the production load and see how the performance is. When we did the testing for our production workload, we saw that our write latencies were doubled, and the read latencies were even more than double for the new system. And our canaries also failed us to promote the new system. So basically, we were shocked, like, what just happened? The new system is supposed to make our life easier, but what we are seeing is the worst performance. Then we thought, okay, let's try to figure out what is the difference in the execution. Like, what's the CPU difference? What is the properties difference in the both systems? When we did the CPU profile analysis, we realized that the nodes running on Cassandra 4 were misconfigured to use the CMS garbage collector in place of G1 GC. They were also misconfigured to use a Sun security provider, which is relatively slower for the Netflix environment. And then when we verified for the Cassandra 3 nodes, we realized that they were configured to use Amazon Corretto crypto provider, which is significantly faster. So these are the few differences which we realized from the CPU profile. We also realized that we are using the heap percentage usage in Cassandra 4 nodes was more. And then we figured out that there are few heap settings difference in the configuration. And there were also a lot of hints were getting piled up because in Cassandra 4, we were throttling the rate at which hints can be transferred to the other nodes. So after doing all this debugging, we figured out that Cassandra is not the problem, it's the Netflix configuration. So we tried to fix the Netflix configuration for Cassandra 4 and tried to monitor the performance of it. Once the configuration has been fixed and we monitored the performance, these were the results. If you see, the red line denotes the Cassandra 4 performance, and the green is Cassandra 3. So there was a significant improvement in the latencies. The reads in Cassandra 4 were even performing way better than Cassandra 3, and the write latency is at par what we were observing in Cassandra 3. Then we waited for our canaries to give their result. And we passed a performance evaluation with the flying colors, and we finally we did the in-place upgrade of the cluster in this case. Now, Joey will talk about thrift to SQL migration.
Thanks, Ayushi. I just want to point out, one of the things I'm so proud about those kinds of issues, nobody at Netflix knew about them. The data platform team was the only one who had defined and fixed those issues. The application teams were never impacted because of the shadowing. This capability to not impact the app teams became especially important when we undertook our thrift to SQL migration. And this was where we tried to upgrade our Apache Cassandra 2 clusters to 3.0, so then they could be upgraded to 4.0. I think we might be seeing kind of a pattern. Why? Well, because Thrift was deprecated in 2016, last I checked, it's 2023. We really should get on this. We're kind of behind. But why hadn't we done it? We hadn't done it because it was really scary. Between Cassandra 2 and Cassandra 3, the entire storage engine got rewritten. As we tried to upgrade a couple of test clusters from 2 to 3, we started seeing data corruption issues because of our use of Thrift, and the 3.0 storage engine wasn't particularly well tested with Thrift. So we were very concerned about this upgrade, so we kept kind of putting it off as much as we could. In 2023, we decided to tackle this head on. We were going to shadow traffic to over 200 databases. We were going to backfill using our strategies, and we're going to use these massively parallelizable and reproducible parity check systems. How'd it go? Well, again, we defined a couple of migration paths. And we started with trying to define, to really, at Netflix we call this paving the path, which means that we kind of try to make something really easy for people to use. And in this case, we paved the path of migrating via the data gateway. This was kind of our recommended option for most users. And in this world, folks would actually call into the data gateway. So they would do an API migration, but they wouldn't do a data migration. And then the API server, the data gateway, would translate between Thrift and CQL. And we'll see how this kind of decoupling is really helpful later. For us, it was really important because it allowed the application teams to make their code changes without migrating all of those thousands of terabytes of state. At least the time that we had started this project, we didn't have those offline comparison systems that Ayushi was talking about. So we didn't know how we were going to verify petabytes of state. So this allowed our app teams to move quickly, finish their API migrations, and then the data platform team could later go back and finish the data migration on our own pace once we had the tooling in place. There was a secondary path, though, and that secondary path was using a library. Here we see that a client service couldn't use the gateway. Maybe they were using some complex Thrift feature that we didn't want to support in the gateway. And so for those use cases, we kind of call it white gloving, which is where we kind of help those users one-on-one. White gloving doesn't really scale very well, but if you use it as a backup path, it can help you kind of not have to build more complexity into your abstractions. All right, so what does it look like? Well, this was the migration campaign, over 200 applications, and this is kind of the burn down over roughly 2 years. And you can see that we were able to achieve a large number of migrations very quickly. And that was because of this use of the API migration separating from the data migration. Those teams were able to finish their migration, and then we were able on the data platform to later move the data for them. And all of those ones over there that are like red, like all of those are the bespoke library-based migrations, right? Because you have to actually get the app team to build those implementations because they have something special, right? So one thing that we try really hard to do on the data platform is get as many folks onto that paved path so that we can we can kind of take the pain of the data migration for the app teams. But along the way, what bugs did we find? I always love these because I think it shows the value of having that kind of shadow system in the comparison system. What are some bugs? Well, we found a pretty serious regression in multi-hash key scanning. In the Thrift implementation of Cassandra, multi-key reads happened in parallel. So if somebody requested 100 hash keys, they'd get back all of the 100 at once in one lookup. In CQL, the upstream had changed it so that coordinators batch by coordinator, and then they execute them sequentially. So if you have a cluster with 100 nodes, this can make your query up to 100 times slower. This was pretty unacceptable. The user was like, hey, I can't do this migration. The latency would go up by a factor of 8. Luckily, because we control that gateway, we don't have to go convince the Apache Cassandra community to change the implementation in the coordinator. We can just fix it in the gateway. We just implemented parallel reads on our own, and we're able to bring that latency back down. And importantly, this happened without app teams knowing. We detected this in our canaries. Our canaries failed. 800% regression is an unacceptable regression. Canaries failed. We were then able to identify the issue and then resolve it. And this is one of the really powerful things about having that abstraction layer, is that you don't have to get your data store to agree with you. You can just fix it. All right, so we found a multi-partition read regression. What else? The next issue that we ran into was significant differences in how Thrift and CQL implemented pagination. In particular, Thrift, as we had it configured for this particular use case, didn't implement pagination. So if you asked it for a row that had 100 megabytes of data, it would return you 100 megabytes of data. And this is a problem because key value, we talked about earlier, returns data in like 1 to 2 megabyte pages, order megabyte pages. So this meant that we were doing 100 megabytes of work times 100. For each page, the key value server was retrieving 100 megabytes out of the backend data store. So like, accidentally quadratic, kind of a bummer. So this also failed our canaries. What was the solution? Well, again, we control that gateway. We control this behavior. So we can detect that we have these large partitions, and then we can kind of dynamically scale down the amount of data that we're asking for in subsequent pages. We call that auto-tuning page size, up and down based on the first page. And we're doing that to try to limit the rows fetched to get about 1 megabyte. So yes, maybe we do that 100 megabytes of work on the first page, but we don't do it 99 more times. And this fix was enough to bring the latencies back in check and unblock this particular application from migrating. All right, so multi-partition read regressions, pagination inefficiencies. What about scan? Oh, scan. Scan was full of so many problems. Scan across promotion was very frustrating because the two data stores don't provide the same sort order across hash keys. That's because Thrift used something called the random partitioner, which essentially is just taking an MD5 hash of the key, and then that's how it locates a 120-bit token on a ring. CQL, on the other hand, had quite intelligently moved to the murmur3 hash, which is faster and produces a nice 64-bit hash token. But this is problematic when you're trying to shadow scans across these two data sets. In particular, if you had a primary that was Thrift and you were shadowing the same scan to CQL, the CQL implementation would decode the page token and would see a 120-bit hash token and be like, well, that's a completely invalid ring position. So the scan would go to a nonsense token. Even if you normalize the tokens to 64-bit, they still went to the wrong place, but at least they went somewhere that wasn't an error. But more problematically was as clients, scans at Netflix across terabyte data sets, those can take hours, right? Scans aren't a fast thing. So a client could initiate a scan against the Thrift implementation, and then halfway through, if we promoted that, then they would all of a sudden start scanning somewhere totally different in the CQL implementation. So that'd be really bad, because then the user would be getting incorrect results back halfway through. Also, can you imagine debugging that? Right, someone comes into your help channel, and they're like, well, halfway through my scan, I just started getting totally random stuff that I already gotten before. Right, it's a really tricky bug to debug, and we didn't want to have to. So we needed a solution to this kind of scan across promotion problem. All right, so how do we solve that? Well, first, we normalized tokens. So I talked about earlier about how your API has to kind of bring resumability into it. In this case, we did that by normalizing the tokens within the scan itself to something that could be translated with high fidelity to both implementations. And then in order to make the scan across promotion problem go away, we basically informed the client when they started a scan, we informed them, you need to continue your scan against this implementation. So you can see here that the scan items is sending this use data abstraction layer Thrift with this token. And then that tells the gateway, regardless of who you think is primary, you need to keep sending the primary for this particular query to this implementation. So with that, that kind of wraps up some of the bugs. We talked about all of these kind of complicated performance problems, and all of these were different use cases, right? When you have hundreds of applications, you're going to run into some sample of issues. But again, really key to this is that our application developers didn't know, because the data platform team had all of that insight into the shadow, and we knew that those performance problems were there, and we knew that those correctness problems were there before we did any promotions. All right, with that, I'll hand it back to Yushi to close us out. Thank you.
So another migration which we did at Netflix is the Dynamite to key value pair. So Dynamite is a Netflix implementation of distributed Redis data store. And why was this migration required? Because when we evaluated the performance of Cassandra connected with cache, EVCache, we saw that the performance is way better than what Dynamite is giving to us. So we carried out this migration. The major concern with this migration is that the user was very sensitive to the low latency, and during this entire migration cycle, we cannot afford to degrade the performance. We use shadow reads and write to carry out the migration for this, and also all of the data is marked as TTL, so we didn't have to copy the data from old database to new as a part of a backfill. We just decommission the cluster once the data has reached this TTL. So this migration was carried out via library, where the library basically takes care of writing it to key value and dynamite at the same time. So what bugs did we find in this migration? None. Sometimes migrations are not painful. So it really worked for us, and I think the major reason for us it worked because most of our use cases were already supported by key value, and also the data was set with TTL, so we didn't have to move data, and this is reduced the correctness bugs in that case. So during all these migrations, we had few key takeaways, and we want to discuss those with you. The first is, migrations can be complex, time-consuming, but with proper automation, you can really simplify them. It can highly speed up the process and reduce the human error and give us our important time back, which we can focus on other important tasks. Second, the new versions can have correctness and performance bugs, but it's up to us to do the proper evaluation. We should do performance evaluation, unit testing, and integration testing to be sure that, okay, the new system is working as expected before we promote it to the production environment. Third, we should always avoid doing API and data migration together. Isolating them can help us in debugging the issues properly. Let's assume like if you are doing API and data migration together and there's some issue, like it's very difficult for us to find out the source of the cause. And lastly, we should prefer homogeneous migration over heterogeneous migration because data mapping is easier in homogeneous migration as the data structure or system is similar across the platform and there are less compatibility issues. That's all from us. Thank you for taking out your time and listening to us.
Thanks again.